Okay, so here's the next thing for us to talk about. So last time we were talking about lines and planes. There's different ways to represent lines and planes in different contexts. Then there are some associated puzzles that come up. So, for example, suppose you're given two lines that go through the same point, right? And you want to find the equation of the plane that contains both of those lines, right? So you got a line through that point, another line through that point. There's going to be a unique then plane that contains both. So how do you find the equation of that plane? Okay, so what I advise is translate to the language of geometry, right? So the things that you're given, if you have the equations of two lines, the parametric equations of two lines, think in terms of what geometric objects does that give you. Then, for the equation that you're looking for, the equation of the plane, what geometric objects do you need? So don't think of it as how do you go from this algebra to that algebra. Translate the question into how do you go from these known geometric items to these other known geometric, or these other hopeful geometric items. So, for example, in this case, you've got a parameterization, two parameterizations given to you, and you want to find an equation. Okay, wait a minute. That first parameterization, think of that as you have a point and a vector that you think of as geometric objects. That's what you want to think of. What do you get from that parameterization? Likewise, for the other parameterization, you get another vector. So that's what you're given, right? Okay, now question, what do you want? You want the equation of the plane. Okay, yeah, but that's algebraic. Think geometrically. Geometrically, what do you need? Well, you need, I need to know a point on this plane. Okay, that's going to be an easy one. I'm given a point on the plane, in effect, from the parameterizations, right? And I also am going to need a normal vector, and a vector perpendicular to that plane. So that's the other object that I need. So forget about the equations. Now, at this point, it becomes a geometry puzzle. Given these geometric objects, how do I find those geometric objects? And the first thing that'll leap out at you is, I'm given two vectors parallel to the plane. I want to find a vector perpendicular to the plane, and of course the cross product is the thing that's going to do that for you. And everything else is details. Yep?
What's the question asked to find the continuous line? Isn't that finding their angle?
Well, so we want to find the equation of the plane, and the equation of the plane is n dot x equals n dot x naught. So you need that n. Yeah. Right. Yeah, I probably should have written the question more explicitly in that sense. Yeah. Right. Okay, here's another example, and I'm not going to work out these details, for these examples. I just, kind of want to talk strategy. The details you guys can do. You have all the detail tools from the last lecture. Okay, given the equations of two planes, let's say this and this, for example, how would you find this line of intersection of those two planes? Right. So now, again, you could think of this as, we've been given two parameterizations. We want to find we're given two equations of planes. We want to find a parameterization. So let's translate that into geometry. Given two planes, you can infer from each equation that you're given the corresponding normal vectors. Right? Again, you just read those straight off of the equation. Right? So we're given these two normal vectors. What do I want to find? I want to find a point on this line. I want to find a vector parallel to the line. Those are the two things that I want. And again, now you sort of have a geometric point of view on the question, and you can start, playing the appropriate games. Usually the hardest question is to, find that vector. That vector you'll see being parallel to that line, the line being in both of the planes individually being perpendicular to the normal vectors. You think it through. Not hard to persuade yourself that blue V vector that we're looking for needs to be perpendicular to both N1 and N2. Right? And so, again, cross product then is going to, as it turns out, going to be the thing that allows us to get such a vector. And then to the question of, well, how do you find that x naught? This actually is going to be an algebraic process, and you just solve the pair of equations. And so, eliminate a variable, etc. Okay. All right, last one, and I want to do this last example because there is something particularly challenging about this one, and I think this is a homework question, or this is closely related to a homework question, or anyway, it's definitely going to be relevant for your homework. Given two lines, find the plane that's parallel to both. Now, wait a second. Given two lines, there's lots of planes that are parallel to both of those lines. I want to find the one that's parallel to both and equally distant from both lines. All right, so this is a little bit tricky move here. So you can translate into geometry and think about what do you have, what do you want. Play the usual games. Not hard to persuade yourself that if you are given a couple of parametric lines, right, then you have those vectors. Real easy to persuade yourself that the normal vector is going to be the cross product. That's easy, right? So the big question is, how do we find a point in this elusive plane that we're looking for? How do we find that point right there? And the assertion that I'm going to make is that if you just take the midpoint of the line segment connecting the two given points in the lines, that will do it. So x1 plus x2 over 2. Now, we have to justify this. We can't just assert, I claim this works and walk away, right? So how do I know this works? This is what's a little tricky. I'm going to explicitly compute the distance from this line to this plane. And I'm then going to explicitly compute the distance from that line to that plane. And we're going to prove that those two distances are equal, right? If you use this formula. So here's how that calculation goes. First observation, because this is the midpoint of that line segment, that vector and that vector are clearly the same vector. Yeah? I think that's pretty clear. You can algebraically confirm this by taking x1 minus x naught, and then also computing x naught minus x2. Keep in mind x naught is this formula. That will confirm my assertion. Okay, easy algebra there. Okay, so step one, how am I going to find the distance there? Well, that distance, I'd like to observe, is the same as that distance, where I've, tied that to that. And that is part of a little triangle here. Right? And this green distance that I'm looking for here is, it's a certain component of that purple vector. By the way, let's give that purple vector a name. Let's call it, I'm going to call it H, because it's half of the difference vector. Right? We can call this one H as well. Okay, so that green distance that we're looking for is a component of the H vector. Now, specifically, it's a component in a certain direction. It's the component of that vector in the direction perpendicular to n, and my picture is poor, but in the normal vector direction. So it's the n component of H. Everybody on board with that so far? Alrighty. Yep.
So don't planes extend indefinitely?
Oh yeah. So the definition of the distance from a let's say a point to a plane is, there's lots of points in the plane and arguably lots of distances, right? What we call the distance from a point to a plane is what is the shortest distance. And then I'm going to argue with geometric intuition. The shortest distance is also the perpendicular distance.
Okay.
Yeah.
But if it's parallel to the planes, shouldn't it be?
Well, the line is parallel to the plane. So we've got a line here, and we've got a plane that's parallel. The distance between the parallel line and the plane is going to be the distance from any point on the line to the plane, and that's going to be something like this. Yeah.
Okay.
Yeah. Feel free to ask me after class if you have other. Yeah. Okay. Yes.
So if the vector is the shortest distance, should it be already perpendicular to the plane? So already parallel to one another?
Yeah, this green distance that I'm looking for here, yeah, that's in the direction of this normal vector, and apologies for my picture not being very, very accurate. Yeah. Yes?
No, but I think she's asking, like, shouldn't the green vector and the purple vector already be the same thing?
Oh, no. Oh, yeah, no, not at all. So you got to keep in mind these 2 points that we were given here. These 2 points, x1 and x2, these 2 points here are just kind of random points on those lines, right? I mean, who knows that they were just, from some parameterization we were given, and there's no promise that those are somehow, the magically, those right special points. Right, absolutely, yes.
Can you go over how we know that the distance between them is the same then? Because I thought when they say equidistant, it would be the the perpendicular, so that's how we know that.
So I understand. Tell me your question.
Like how do we know that both of those vectors are the same from x1 to x0 and?
Oh yeah, because simple algebra. I mean, just you can do the algebra for yourself, but take x1 minus x0. Here's your formula for x0. Right? And then secondly, do x0 minus x2. Here's your formula for x0, and you'll just get the exact same formula. Right? But intuition-wise, it's because I'm taking a line segment and cutting it in half. Right? A line segment, you might say, has a direction, right? And so you cut it in half, those 2 pieces are still pointing in the same direction. I cut it in half, they have the same magnitude, yeah.
So the lines don't intersect, right?
Correct.
Okay.
Correct, yeah. If they intersect, then yeah, just you take the point of intersection, and it reduces to that previous question that we already considered. So here, there's no such assumption, and so, let's play like they don't intersect. I mean, if they do, this still works, but let's assume that they don't. Worst case scenario. Okay, so we've computed this green distance. Right now, the assertion is that when you pick this formula for x0, my assertion is that makes both of these distances the same. We just computed that one. Let's now compute this distance there. That's the perpendicular distance from x1 to the plane. And how do we compute that? Well, here's the thing. It's a component of that purple vector. That's still h. It's still a component in the direction perpendicular to the plane. It is the in component of h again. So, same formula, same value. Therefore, these 2 distances are equal, and therefore this is the right plane. So anyway, clever argument that has to be made, insightful choice that has to be made for what that x0 point is, and I just wanted to show you all how this trick works. You're going to need something kind of like this on the homework. Okay, alrighty. So moving along, let's see. I wanted to switch back to Okay, we're going to talk about parametric curves now. We've seen parametric lines. Well, parametrizations of lines. The term parametric line means a line for which you have a parametrization. Right? So parametric curve, same thing. It's a curve for which you have a parameterization. And don't forget what a parameterization was in the context of a line. It says I just want to know position on the line as a function of some parameter, t, which very often we think of as time. So a parameterization of a curve, same deal, position as a function of, think of it as time, right? Except now you don't have to go in a straight line. So here's an easy example of a parametric curve. Look at those equations, x equals cosine t, y equals sine t. Now notice that gives position, x and y, between them, tell you position, for any given point in time, right? Both of these coordinates, x and y, are functions of a single variable time, or t, which again we're thinking of as time. Okay, so position as a function of time. And you can start plugging in values, right? Plug in t equals 0, plug into there, out comes a certain point, namely that point. Plug in t equals a half, well, plug into the equations, out comes an x and a y, namely a point. Right? And repeat, do this all you want. For any given value of t, there is a corresponding location. And therefore, intuition goes, as time passes, as t increases, right, this point is moving, and it's, you might say, tracing out that curve. Right? So that's not that different, again, from the idea of a parametric line. It's just not necessarily straight. And but the same sort of structural idea. By the way, a notational thing, because we think of this x and this y as giving position, and because we group coordinates into an ordered pair to think of them more explicitly as position, sometimes we'll write the parametrization like this. So x and y, both functions of t, and here is that vector position then, as a function of t. And then in recognition of the fact that x comma y is a vector, you could just give that a name, put a little vector arrow over it, and I like to call it x vector of t myself. And that's so again an alternative notation. By the way, another common choice, the book likes to use r to represent x comma y. That's very common. I don't personally like it because we're going to find r is it's an overused letter. R represents a polar coordinate. Some of you all have seen polar coordinates before. We're going to talk about polar coordinates later, but anyway, if you've already seen it, then you know what I'm talking about. So it's already that. It's also very often used to represent a radius of something. We're going to find that we're dealing with a lot of round things in this class, and so lots of radii. So anyway, I feel like r is overused, so I like to call it, x, suggestive of these coordinates by virtue of that being, in fact, one of them. Okay. So there's your first parameterization. Now, this one, I claim this traces out a circle. How do we know this traces out a circle? Aside from, well, I remember my trig class. Right? Well, an easy way to confirm that this traces out a circle is to note, well, in fact, this x and this y satisfy this equation, right? I mean, plug them in, it works. Now let's think about what that means. I mean, what do we interpret from that? What we interpret is that every point created by this parameterization, because it satisfies this equation, means that every point created by this parameterization is on the circle. So this entire parametric curve has got to be on the circle because, well, they all satisfy the equation of the circle. Okay, now that's not quite the same as saying that it parametrizes the entire circle, right? How do we know? I mean, who knows? Maybe this only parametrizes one part of the circle, maybe, right? Technically, all we know is it satisfies the equation, not that it traces out the whole thing. So in order to see that this actually traces out the whole circle, just think in terms of what happens as you increase t, and you can persuade yourself just by kind of plugging in that this in fact makes it all the way around the circle. Okay, and we don't need to get more rigorous than that. Okay, here's another one. There's a parametrization. Note that I'm using this notation here. Right. And what that's telling me, reminder, is that this is x as a function of t, and this is y as a function of t, right? That's the, well, here I'm going to do it like this. That's the x, and that's the y. So when you see something like this, position equals, and then, an ordered pair of formulas of t, keep in mind what that means, right? The coordinates are x and y. Okay, so it's not immediately clear what this is, right? I don't recognize that from trig class or something convenient like that. So how do we identify it? Well, I encourage you to try to, bang around and try to find some sort of algebraic relationship between these formulas. Right? So, for example, wouldn't it be nice if this was always twice of this? Right? Then, that would be y equals 2x. Oh, that's a line. Now we're good. Right? So it's not always that easy, but, by kind of messing around, you can usually Well, you can often figure it out. So, for example, let's look at this formula here for x. That's my x. And then look at the formula for y, and notice that that formula for y is not crazy different, right? It's not like the x formula of 2 plus t, and then the y formula is, e to the power of, arctangent of t. It's not that weirdly different. They're kind of structurally not terribly different, right? So think in terms of what do you have to do to the x to get it to look like the y. And so notice I kind of start messing around here. I notice that if I multiply that formula for x by 3, then now this looks at least more reminiscent of that, at least by virtue of this 3t now showing up. It's not exactly the same yet, but it's better, it's closer, right? The difference now is that this has a 6 where this has a minus 5. Okay, well, let's then deal with that. Let's subtract 11 from both sides of the equation. And now, having subtracted 11, notice that this thing that I'm messing with has turned exactly into that, namely y, and therefore I have a relationship between x and y. Everybody see what I'm talking about there? So, something to mess with. Sometimes that will help you out. Okay. Doesn't always work, especially in 3 dimensions. Here's an example. Suppose this is your position as a function of time. Well, gosh, it's going to be really hard to play around with these equations and find a single equation that these all satisfy. I guess technically it could be done, but it's not immediately obvious how you would do it. So what I would encourage you to do here is just kind of think in terms of, let time pass and think about what's happening. What do you notice and what can you conclude from that geometrically? So for example, these first 2 coordinates, I understand. Cosine t, sine t. Oh yeah, we already talked. That's doing this thing, right? It's going around in a circle. Okay, now, are we allowed to just look at those first 2 coordinates? Well, if you look at the first 2 coordinates, right, you have 3 coordinates and you just look at 2 of them. What you're doing is you're saying, I'm going to look at one of these actual points and just look at the projection down here into the xy plane. Right? We're going to forget about the z coordinate, throw that away, look at just the x and the y. That gives you the projection of the xy plane. So what we know then from this observation about cosine t, sine t, the geometric interpretation would be that this curve, whatever this curve is, whatever it's doing in space, its shadow down here in the xy plane is going around in a circle counterclockwise in the usual kind of cosine t, sine t sort of way. Okay, so if we understand the shadow is doing that, and then, by the way, now let's, what else do I know? Well, I can look at just the z-coordinate. Well, looking at just the z-coordinate means effectively you're going to kind of project over here to the z-axis. That z-coordinate, also easy to understand. It's just t. What happens as time increases? What happens to t? Well, it increases, right? So here's what we've got. I mean, complicated geometry challenge to, think about, kind of piece it together in your mind. But we're looking for a curve whose projection in the xy plane is doing this, and where the point is rising in altitude at a constant rate. And then you kind of piece it together, and it's not hard to persuade yourself you get this helix. Yeah? Everybody happy? Okay. Sometimes you have to kind of piece it together like that. Okay, so by the way, we're going to deal more with parameterizations later. It turns out, by the way, parameterization's a really big deal. When we get to chapter 15, we're going to be doing a lot of stuff with parameterizations. We're just kind of getting started right now. In fact, really, in chapter 13, we're going to do a fair amount with parameterizations also. Okay. Alrighty. So let's do our very first calculus. Now, here it is, 3rd week of classes. Very first little bit of calculus. Let's ask, what's the derivative of a parametric curve? There's some philosophical questions here. Like you remember we were first defining, what does it mean to add 2 vectors? And I pointed out that there is no pre-existing definition of what it means to add 2 vectors. So it's not what is the addition of 2 vectors, but what should be the addition of two vectors? Right? Why would it make sense? Right, so we're making choices here. Right? All right, so how should we define the derivative of a parametric curve? Well, golly, that's a hard question. There's different points of view you can take on that. And by the way, no kidding. In this class, we're going to introduce a bunch of different kinds of notions of derivative. Bunch of them. Right? So there is no single answer to, what is a derivative. It's a lot of different points of view you can take. Here's one. A reasonable point of view to take in this context of a parametric curve would be to say, look, I've had a lot of success with this formula elsewhere. Right? And I don't know. Let's try this. Let's see if something nice happens. Lack of any other better ideas. Seem like a reasonable place to start? Okay. All right. So hope everybody recognizes the how much this heavily borrows from the single variable definition of derivative. Okay, so now let's look at what this says in this context. Here you have a difference of two position vectors. So we've got, let's see here, let me color code here. I'll use blue, fine. Okay, so I've got these 2 points on the curve. This says, look at the difference. That's that vector there. There's that difference. Right? But I'm interested not in the actual difference itself, but in, divide that by h. Well, and by the way, h is approaching 0, so h is small. When you divide a vector by a small number, dividing by something small makes it larger, right? So I'm going to draw the difference as being, the quotient there as being a longer vector. And okay, let's just kind of think through what happens in the limit as h approaches 0. That's what the derivative actually is. What I've got here is not quite a tangent vector to the curve. This thing is I guess you might say it's a stretched secant vector, you might call it, right? In the limit, though, you would expect, as h gets smaller and smaller, these 2 points that are defining that initial difference get closer and closer. That initial difference is closer and closer to a tangent vector. Feels like it ought to be a tangent vector. Yeah? Okay, and there's some conditions to be worried about here, but that's not what Math 212 is about. Good news. Most of the time it is. In any circumstances that we need to worry about, it's fine. Okay, so tangent vector. So that tells us about the direction of this thing. By the way, I emphasize, we just wrote this down without any justification other than, I don't know, I don't have any other better ideas, right? So let's not assume that this is going to work out nice, right? The fact that this thing that we've written down algebraically is geometrically natural in at least one way, that's already kind of a victory. Right? There's no law that says that formulas that work out well in one class must work out well in other contexts. Right? So this is good news that we have a tangent vector. Yeah.
So is the length of the tangent vector going to be equal?
Well, yeah. We haven't addressed that question yet. That's the next thing we're going to talk about. Yeah. Right. Absolutely. Okay. So, So what is the length exactly? So we know that the direction of this thing is that it's tangent to the curve, so something, I don't know, kind of like that maybe. Right? So how long is it? What's the magnitude? I'm going to sweep some formalities under the rug. I'm going to say, well, if you want to take the magnitude, here, let me switch to the pencil. If you want to take the magnitude of the velocity, well, then we're taking a magnitude of the limit. Let's commit a little crime here and just move that right inside the limit. In the cases we're interested in, this is fine. And let's look at this formula now. The magnitude of that difference is a distance. It's the distance between those 2 points. Which, by the way, that's the distance as the crow flies, right? It's not technically the distance along the curve, but if this is a smooth curve and as h approaches 0, we can think of this as pretty much the same as the distance traveled along the curve. Right? So distance. Divided by, what is h? Here, h is, well, it's approaching 0. Notice h is the difference in the times. It's the moment t plus h minus the moment t. So it's the elapsed time, the duration, you might say. So this magnitude we're interested in is distance divided by time. And that's speed. Right? So existing physical / geometric concept, speed. And now let me call you all the way back to the very first day of class, and a vector is defined by its direction and its magnitude, right? And we have a pre-existing name for a vector that points in the direction that something is going and whose magnitude is the speed that it's moving in that direction, and that's velocity. Right, so this x prime is velocity. Everybody happy? Okay. All right. Now, that's kind of familiar, isn't it? Anybody remember way back when in single variable calculus that in some context the derivative was interpreted as velocity, but it wasn't always, right? In some other context, the derivative was interpreted as a slope of a tangent line. Right, so what gives? When is it a velocity and when is it a slope? Well, it's all about the context. Most of the functions that you saw in single variable calculus were thought of as were thought of in the context of graphs. So we represent them with the value of the function being height, the input variable being, distance to the right, right? So vertical as a function of horizontal, with no time involved at all. And that's a certain kind of a geometric construction, a certain way of representing a function. And in that context, the derivative is the slope. On the other hand, there is a totally different context, and y'all may recall that, on some occasions, you look at, the x-axis, and you imagine some little car that's driving along. And this little car, maybe it starts there, and then it, travels along some path, has some road trip that it takes along the x-axis here, where position's given as a function of time. And that's a very different picture, right? This is not vertical as a function of horizontal. This is horizontal as a function of time. Very different picture. And so very different interpretation. That position, the derivative of position is velocity. Okay, so if you think about it, that context, this is really just a one-dimensional parametric curve. This is position as a function of time, not where position's given by two coordinates, right? But where position's given by one coordinate, namely where are you on the x-axis. So they don't use this terminology in Calc 1 classes, right? But this is a one-dimensional parametric curve. So you've kind of seen parametric curves before, again, said differently. So not really a surprise. And analogously, second derivative is acceleration. Okay, so here's what we've got. We've got a formula for a derivative. We've got a geometric interpretation of derivative of a parametric curve. And that's all well and good. But how are we going to compute these things? Now let's rewind, think about back to Calc 1. How did we compute derivatives in Calc 1? And the answer is that the very first time we computed derivatives, we had to brute force actually crank out directly from the limit. And it was horrendously inconvenient. And so we pretty quickly moved on to shortcuts. Right? And so y'all memorized a bunch of formulas in Calc 1 classes. The derivative of x to the n is nx to the n minus 1. The derivative of e to the x is e to the x. And the derivative of sine is cosine. You remember all those millions and millions of formulas. Product rule, quotient rule, chain rule. All these different tricks for computing derivatives. All of those formulas were presented, motivated, possibly conceivably proved, but only in the context of derivatives of single variable functions, which is not what we are doing here. We now have derivatives of vector-valued functions. This is a completely different thing. All those old formulas are gone. We can't use them anymore. This is horrifyingly scary. Right? Because, oh my gosh, how are we going to compute these things? So here's the really good news. The good news is that if you look carefully at this formula for how to compute a derivative. And just let's kind of go through the process. It turns out really nicely. There's a difference of two vectors, which, by the way, we know how to do. Differences are computed component-wise. Okay, now the next thing I have to do to this difference that was computed component-wise is I have to divide by a scalar. That's done component-wise. Right? That's just the rule for how you multiply a vector by a scalar. And then lastly, now I've got to take a limit of this vector-valued expression. We have not talked about that yet. I'm just going to assert, and again, this isn't exactly what Math 212 is about, but limits are computed component-wise. And so, for example, notice then that the first coordinate becomes exactly the good old Calc 1 definition of a derivative of a single variable function. And that first coordinate is a single variable function. Right? So, good old x prime. So, good news. This brand new vector value derivative that I need to compute and for which I have no shortcut rules, I can compute it by looking one component at a time at a bunch of single variable derivatives for each of which I get to use shortcut rules. And we're happy again. Everybody on board? Okay, I'm going to have to speed it up here. So there's some algebraic properties that have to be checked. Again, anytime you introduce a new definition, you have to explore, how does it behave, and does it behave the way you would sort of hope that it would? And again, none of these things are obvious. Now, you might look at this and say, well, this is kind of a product rule. Yeah, but the product rule that y'all know was only for single variable functions. Right now, we've got this brand new kind of sort of product thing called the dot product. How do we know that the dot product has a product rule that works? Well, you just got to compute. Right? So you can directly compute both sides of this equation, crank them all out in terms of coordinates. Just works. Right? So all these formulas have to be checked. I would encourage you to check a couple of these. Maybe check one of these because they're relatively easy, and then check one of these because there's a little bit more work involved there. Make sure that you can see how that argument goes. Okay, what about antiderivatives? We talked about derivatives. So how do you take antiderivatives? Well, good news, that's computed component-wise. I mean, if you take derivatives component-wise, antiderivatives, we're just undoing the derivatives, also done component-wise. And so, very conveniently, for example, if you want to know position, right, as a function of time, the fact that velocity is the derivative of position means that position is the antiderivative of velocity. Now there's also this plus c because there's multiple antiderivatives, right? But the point is you can do this calculation one component at a time, right? To find your antiderivative. And then there's the issue with finding the c. We'll talk about that in a minute. I do want to warn y'all against a dangerous thing. A lot of, especially high school calculus classes, conflate the idea of the antiderivative with the idea of the integral. And I mean, I get the point of view, right? I mean, there's a really strong connection between antiderivatives and integrals. Huge theorem, fundamental theorem of calculus, says that you can compute integrals with antiderivatives, which is amazing if you think about it. Okay? But this gets misstated very often as, differentiation and integration are just exactly opposites of each other. That is a gross overstatement and is not true. So be really careful about this. I hope y'all are aware of the distinctions that make these different things. And if you're not, by the way, come to my office hours. I'd love to expand on this and expound and clarify and make sure everybody's clear on that difference. But please, if what you're interested in is undoing a derivative, I strongly encourage you to just think it's an antiderivative, right? Sadly, the notation looks a lot like the notation for an integral, but it's not the same thing. Okay. All right. So now let's talk about integrals of parametric curves. And what is that? And the answer is, it's not clear particularly what this would mean. Let's just explore this idea. Right now, y'all are accustomed to integrals meaning things. Right? You take an integral of a regular, Calc 1, take the integral, you get the area under the curve. Right? I mean, yawn. Right? That is absolutely not what this is. In a Calc 1 context, you're looking at a graph, y equals f of x. If you write down integral from a to b of f of x dx, well, then here's the thing. That represents a height, and that represents a width. And you're looking at height times width, and yeah, that's area. Right? So you can make geometric interpretations of integrals when you're looking at graphs of single variable functions, and that's all fine. Okay. Can you do that here in this multivariable context? Well, no. This here just isn't a height times a width. It's just not. That's not a height. That's a position. It's a vector for one thing. Right? It's not a distance. It's a 3-coordinate position. It's not a height. This doesn't represent a width. It represents a duration. Right? So we are not computing height times width here. So please, a lot of students just make this tragic error of thinking that somehow if you write this down, that would be the form. That would be how you'd compute the area under a parametric curve, and it makes no sense at all. Right? And there's a separate question of, well, and how do you compute the area under a parametric curve? We'll be able to talk about that at some point. Good news is we're actually not particularly interested in that question. Yes?
So if the limit side of that equation represents the sum of like a position times time, does that not represent the accumulation of position?
I don't know what that means though. What do you mean by I mean, we could have a conversation about how might I come up with some geometric or physical interpretation of what that is, and that'd be a separate conversation. I'm just trying to point out it's not area under a curve by quite a bit, and it's also not immediately clear why it's interesting.
Yes, what even is it?
It's I would say it's not worth pulling on that thread. It's just it's not that interesting of a thing. Yeah, right. And anyway, there's. Oh gosh, I'm arguing with myself because I have a lot of things I would love to say about that, but I just don't have time. It's just not that interesting as it turns out. Yeah. Okay, now here is a situation where you might want to take an integral of a vector-valued function. I mean, the fundamental theorem of calculus is still true. One coordinate at a time. This is an easy thing to prove from the single variable fundamental theorem of calculus. That is true fact, right? But very importantly, notice here what we are taking an integral of. We are taking an integral of this thing that is a derivative. Right? So, if you want to think about this geometrically here, you might think of this as being velocity, which is the derivative of position. Right? In which case, what this turns into is an integral of the velocity function. An integral of the velocity vector gives you displacement of position. In other words, ending point minus starting point. So yeah, that's true. But very importantly, notice we're not taking a derivative of the parametric curve here. We're taking a derivative of the velocity. I said derivative. I'm sorry, I meant integral. We're not taking an integral of the parametric curve here. We're taking an integral of the velocity of the parametric curve. And yeah, that does have an interpretation. Right? So, sure, this means displacement. I don't know what that is. Okay. Alrighty. Okay. Moving along. So, easy example here for, y'all will recognize this kind of thing. If you're given acceleration and some initial conditions, how do you find position as a function of time? And it's just a multivariable version of these analogous things that you've seen in high school, except that these were single variable functions. Acceleration was a single function of time, and initial velocity was a single value, and initial position was a single value. So really what you're doing here is just go through that same process. Velocity is an antiderivative of acceleration. evaluate your constant of integration. And then position is an antiderivative of velocity. Compute your constant of integration, and then you're done. Right? It's totally analogous to all those questions that you did back in Calc 1 classes. I do want to remind you of one thing, and that is don't make the mistake of thinking that it just always works out, that your initial velocity is what that integration constant works out to be, or analogously let's see here, I have to zoom out a notch, that your initial position is automatically what this constant turns out to be. Look, it isn't. Right? This is an illusion that gets cast in high school calculus courses because very often in high school calculus courses, this function that they give you is polynomials. And polynomials have a peculiar property, weird, totally unrepresentative property. And that is, if you take any polynomial, and when you take its antiderivative, there will always be factors of t. Right? You think of any polynomial, every term is going to have a factor of t once you take the antiderivative. And then when you plug in t equals 0, it goes away and turns into 0. That is weird and grossly unrepresentative of how everything else works. Right? So, where does this integration constant come from? Well, so this equation here, velocity is antiderivative plus integration constant. It turns into that. Well, if you've selected a magic function that makes this always 0 when t equals 0, then this thing here will just magically go away, right? And then, it will appear to turn out that that the initial value is the integration constant, right? But as you can see here, that's not always going to be 0. That's not always going to go away because we're not always dealing with polynomials. Okay, so anyway, I cannot tell you how many times I see this on exams that students will not go through this process and students will just say, I'm just going to, okay, so there's my integration constant and then moving on, right? It's not just arithmetically wrong. It's conceptually terribly wrong, right? So the fact that, my numbers are off a little bit is not the point. The point is that it is a gross missing of the concept. Right? So this mistake is going to cost you a bunch of points. And I want to make sure nobody steps on that landmine for lack of awareness. Okay. All right. So there that is. Okay. Moving along to curvature and acceleration. So this is section 12.6. We're going to go really, really quickly through this section. There's there's way too much material in this section for us to fit into Math 212. We just don't have time in the curriculum. There's some cool calculations. They're neato. I like them. They're elegant. And we just don't have time. Right. So I'm going to hit the highlights. That's what Math 212 does. We go through, we hit certain highlights. When I'm done talking about what I consider the highlights, I'm going to identify for y'all what you're responsible for knowing and what you're not responsible for knowing. Okay, so starting off, if you have a parametric curve, we can write down this easy little formula there, right? Looks familiar that we write this kind of thing down in single variable calculus classes all the time. Really, in this case, all this is saying is that your linear estimate of your change in position. Remember, x is your position. A differential is a linear estimate of how that changes, right? So this says, this is what we call your differential position, is computed by, velocity times time. And I think that's extremely plausible, right? That if at this point you know what your velocity is, and then if you multiply by some amount of time, that would give you an estimate of how you displace over that amount of time. Right? It's not exactly right. It's not the actual displacement, but it's your linear estimate of displacement. Okay, so we're going to use this thing dx a lot. There it is. It's that vector. Here's the formula for it. Not hard to persuade yourself that this distance, ds, is just the magnitude of that dx vector, which then easily computed as speed times time. And by the way, just a notational comment. The magnitude of the velocity vector, there's a lot of pencil lead, in saying v vector bar, right? It's when you don't put the little vector symbol over the velocity vector, this is understood to be the magnitude of that velocity vector and its speed. Okay. All right. Okay, and I guess I'm out of time, so we'll call it quits there and catch up another day. All right, see y'all later. Oh, I owe you homeworks. If you'll stick around for a minute, I'll pass back